Welcome to this third lecture on the fundamentals of transport processes. Last class we were doing dimensional analysis and we will continue that in this class, basically to see how dimensional analysis can be used to advantage in reducing the number of variables that are of interest in a problem. Last class we had looked at the fundamental dimensions: mass, length, time, temperature, amperes and candela. And these four, the mass, length, time and temperature, are the fundamental dimensions that we will be using in this course. And then we looked at some of the derived dimensions: velocity, length per unit time, acceleration, rate of change of velocity, length per time square, force, work, energy, power, and some quantities of interest to us in this course. The stress, the viscosity. Viscosity is given from the Newton's law for stress. Stress is equal to viscosity times strain rate. So, viscosity has dimensions of stress times time. Okay. Mass flux, and from Fick's law for diffusion one can calculate what is the dimension of the diffusion coefficient. Dimension of diffusion coefficient is length square per unit time. And then we looked at some quantities of interest in heat transfer: the heat flux, the specific heat, the thermal conductivity. And the thermal conductivity comes from Fourier's law for heat transfer. We used dimensional analysis to estimate the drag force on a sphere settling in a fluid. We first listed out the fundamental quantities that are of interest in this problem. The force on the sphere obviously depends upon the speed with which it is moving. It depends upon the radius of the sphere and the viscosity and density of the fluid, as well as the length of the holding tank. And we got three dimensionless groups. One was just the ratio of lengths. This is a dimensionless group that will recur again and again in this course, some ratio of two characteristics lengths in the problem. The other two were the non-dimensional force. Force, you will notice in this scale, has been scaled by the viscous scales. Okay. So, it has been scaled by some viscosity times the velocity times the radius. Okay. And the other dimensionless group was the Reynolds number, ratio of the inertial and the viscous forces. I said in the limit, when the Reynolds number is small, the inertia should cease to be a parameter in the problem, and therefore, you should get the force just in terms of the viscous stresses, and from that we got Stokes' law, okay, for the force in the sphere. And then we were looking at this problem of heat transfer in a heat exchanger, a slightly more complicated problem. And you have a tube, a hot fluid injected into the tube side of this heat exchanger, and the cold fluid comes out and it is cooled by contact with the coolant. And if we were to analyze the system as a whole, then what we would look for is the average heat flux across the tube surface, okay? Because the total heat transfer rate divided by the area of the surface gives you the average heat flux. So, rather than work with the total heat that is transferred per unit time, we could look at the average flux, which is the flux per, which is the heat transferred per unit area per unit time. And that has to be a function of the average temperature difference between the inside and the outside fluid, the temperature difference delta T that I have written down here. Okay. And of course, it depends upon the thermal properties: the specific heat, the thermal conductivity, the diameter of the tube, the length of the pipe. The diameter and length are going to play an important problem because they determine the surface area and the length of contact between the two phases. Okay. And you will see immediately here the ratio d by L appears as a dimensionless parameter, similar to d by L in the previous problem. Even though the transfer across the surface is taking place by heat conduction, the transport of heat, okay, away from the tube, from the inner fluid to the wall of the tube is taking place due to both conduction and convection. We had looked at the two fundamental processes in the last class, conduction and convection. Convection brings in heat at the inlet and takes out the cold fluid at the outlet. So, heat is brought in to the heat exchanger at the inlet due to convection, and then it is transported across the surface due to conduction. Convection is the transfer due to the mean flow of the fluid, and that is going to be affected by the flow properties, okay, specifically the fluid velocity as well as the density and viscosity. Density determines the inertial stresses in the flow, and viscosity determines the viscous stresses. Okay. Now, if I were to write the dimensionless dimensional variables in terms of the fundamental units as I did in the last class, what I would write is that Q is equal to m L power minus 3. The specific heat is equal to m L T power minus 3 theta inverse. The thermal conductivity is L square T power minus 2 theta inverse. Okay. The temperature difference has units of theta. Tube diameter is L, density is m L power minus 3. The viscosity is m L inverse T inverse, and the fluid velocity is L T inverse, and the length of the pipe is L. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 dimensional groups. And how many dimensions are there? There are 4: mass, length, time, and theta. So, you ought to get 5 dimensionless groups. Okay. At the end of the last class, I also told you that one can simplify the problem further. If there is no transport of energy from thermal to mechanical energy, okay, that is, if energy is not converted from fluid flow to heat by fluid viscosity or vice versa, if there is no conversion of energy from mechanical to thermal energy or vice versa, then thermal energy and mechanical energy are separately conserved. Okay. Therefore, I can consider thermal energy to be a separate fundamental dimension in this problem, okay, because the thermal energy is conserved by itself. It is not being converted into mechanical energy. Therefore, the heat dimension can be written as H, okay, in which case now I have 5 fundamental dimensions, 9 dimensional groups, which means I should have 4 dimensionless groups. Okay. So, let us see what those are. So, if I consider H also as another fundamental dimension, okay, then I should write the thermal quantities in terms of H. Okay. Heat flux is heat transported per unit area per unit time. Okay. Heat flux is heat transported per unit area per unit time. Okay. Specific heat is the heat contained in per unit volume of fluid. Okay. So, I can write it on the basis of delta H is equal to m Cp delta T, okay, which means that Cp has dimensions of H m inverse theta inverse. Okay. So, specific heat has dimensions of H m inverse theta inverse. Okay. Thermal conductivity. Thermal conductivity comes from Fourier's law for heat transfer. Okay. Thermal conductivity comes from Fourier's law. Q is equal to K delta T by L. Okay. So, therefore, K has dimensions of H L power minus 2 T inverse into L theta inverse. Okay. So, this has dimensions of H L inverse T inverse theta inverse. Okay. And temperature has dimensions of theta as usual. Okay. Tube diameter has dimension of L as usual. Density is a mechanical quantity. Okay. Density is a mechanical quantity. So, it has dimensions of m L power minus 3. Okay. The viscosity has dimensions of m L inverse T inverse. Fluid velocity is L T inverse, and the pipe diameter has dimensions of L. Okay. So, now I should have 4 dimensionless variables. Okay. One of these is pretty easy to see. Okay. The fourth one is just L by D. Okay. One of these is pretty easy to see, L by D, and the third one is what we had determined before, okay, in the previous problem, the Reynolds number. Okay. We do not have to do it all over again. Okay. Now, the two others involve the thermal quantities. One of these has to involve the heat flux, which is what it is that we are after. Okay, we want to know what is the flux, average flux through the surface. Okay. So, we can get one other dimensionless group, okay, which involves the heat flux Q. Okay. So, let me just rub this off. Okay. So, the dimensional groups that we will involve are the heat flux Q, okay, and I can choose 3 others, okay, because Q has dimensions of h, l and t. Okay, Q has dimensions of h, l and t. So, I have 4 groups with dimensions of h, l and t, then I can create a non-dimensional group. Okay. Now, actually you cannot find 4 groups with dimensions of h, l and t. Okay. The heat flux can depend upon the thermal conductivity K with dimensions of h, l inverse, t inverse, theta inverse, as well as the temperature difference theta. Okay. And then I have to have 2 other groups of having length and time. I can choose those as d and u. Okay. So, now I have 1, 2, 3, 4, 5 dimensional groups and 4 dimensions h, l, t and theta, and from these I can construct a dimensionless group. Okay. Let us look at what that dimensionless group should be. Okay. So, I have to have q times k power a, delta t power b, d power c and u power d has to be dimensionless. So, it has to be h power 0, l power 0, t power 0, theta power 0. Okay. And we do it the same way that we did it for the problem of the force on the sphere. Okay. So, this q is equal to h l power minus 2 t inverse power a into h l inverse t inverse theta inverse power b theta power c, sorry, let me just power a, theta power b, l power c and l t inverse power d is equal to h power 0, l power 0, t power 0 and theta power 0. Okay. So, now I have 4 simultaneous equations and I can solve them for the 4 unknowns. Okay. And what I will get if I solve them is a dimensionless group which goes as q d by k delta t, okay, which is the first dimensionless group. Okay, q d by k delta t. Okay, one can solve it and see. Okay. This is the first dimensionless group. Okay. Now, I said there are 4. The second one was the Reynolds number. There was one which was just the ratio of lengths. Okay. We got the first one which is q d by k delta t, okay. And there should be a 4th dimensionless group. Okay. Now, that 4th dimensionless group has to involve the specific heat, because the specific heat has not yet appeared in any of the dimensionless groups that we have used so far. Okay, because the specific heat is an important quantity. It has not appeared so far in any of the dimensionless group. That means that the 4th dimensionless group has to involve the specific heat in some way. Okay. Specific heat involves both thermal quantities. Okay, it has an h in it and it has mass in it. Okay. So, therefore, you should be able to get a dimensionless group involving the specific heat, one thermal quantity, okay, and one mechanical quantity. Okay. In this case, I can choose the viscosity without loss of generality as a mechanical quantity, and then I will get the 3rd dimensionless group as Cp times mu by k. Okay. Just by dimensional analysis, you can check that this is correct. Okay. So, pi 3 is equal to Cp mu by k. Okay. So, now for this problem I have got 4 dimensionless groups, okay, and I can write the average heat flux simply as a relationship between these 4 dimensionless groups. Okay. So, I can write this pi 1, q d by k delta t is equal to some function, okay, of rho u d by mu C p mu by k and d by L. Okay. So, now I have only 4 dimensionless groups to vary, and by varying these 4 dimensionless groups suitably, I can find out what the relation is between the heat flux and these other quantities. Okay. So, I have reduced it to a parameter space involving just 4 parameters. In the initial case, I had a parameter space that involved a total of 9 parameters, and if I wanted to find a relationship, I would have to vary each of these 9 parameters independently in order to get a relationship. Now, I have reduced it to just 4 parameters, and I can vary these 4 parameters independently to get a relationship. Okay. These numbers have names. Okay. This q d by k is called the Nusselt number. Okay. The Reynolds number rho u d by mu, and then I have something called a Prandtl number. C p u by k. Okay. And then there is d by L, which is a ratio of 2 lengths. Okay. Now, beyond this, it is difficult to proceed just based upon dimensional analysis. You cannot further reduce, you have to do experimentation. Okay. And the experiments have been done, and they produce what are called correlations. Okay. Correlations which tell you how the Nusselt number varies with the Reynolds number and the Prandtl number and the aspect ratio. Okay. Now, these correlations are based upon extensive experimentation, and they depend upon the flow regime within the tube. Okay. There are 2 regimes. One is for a laminar flow, and the Reynolds number is less than about 2100. Okay. So, when the Reynolds number is less than about 2100, you have one set of correlations that apply. Okay. And these correlations are of the form Nusselt number is equal to 1.86, Reynolds number per 1/3, Prandtl number per 1/3, d by L per 1/3. Okay. So, this is a correlation that applies for a laminar flow when the Reynolds number is small. Okay. And this once again is based upon extensive experimentation, and in heat transfer problems very often the viscosity of the liquid depends upon the temperature. Okay. So, if you have heat transfer from the fluid inside to the fluid outside, then the viscosity at the wall will be different from the bulk viscosity, because the temperature at the wall is different from the temperature in the bulk. Okay. And to take that into account, there is usually another correction factor that is put in, and that is the ratio of viscosity at the wall to the average viscosity, 0.14. Okay. So, this is an empirical correlation that is derived. Okay. For turbulent flow, and the Reynolds number is greater than about 20,000. Okay. The relation between the Nusselt number and the Reynolds number and the Prandtl number is given by what is called the Sider-Tate correlation, and that is of the form Nusselt number is equal to 0.023. Okay. Re power 0.8, PR power 1/3, mu by mu q power 0.14. This should be mu by mu w power 0.14. Okay. So, these are empirically derived correlations. We got to the stage of finding out what are the parameters, the Nusselt number, the Reynolds number, Prandtl number, and the aspect ratio. Up to that stage, we got to just by dimensional analysis. To go further, either you have to do experimentation or you have to look at these correlations. In this course, we will try to see how these correlations can be derived from a fundamental analysis of the combined heat transfer and fluid flow. Okay. Can we derive these? In some cases we can. In laminar flow, for example, we can show why this power 1/3 is coming in all of these correlations. Turbulent flows are much more difficult. In laminar flows, you have nice parallel streamlines, the velocity profile is parabolic. In turbulent flow, on the other hand, It's highly chaotic with eddies of all dimensions, and because of that it's much more difficult to analyze. But you'd like to get some physical understanding for why relations of this kind arise, okay, in these systems. So let's look at dimensional analysis of another system, okay, and that is the reactor system that we had talked about in the very first lecture. If you recall, we had a reactor in which there were catalyst pellets, and the reaction was taking place on the surface of the catalyst pellet. Okay. Now, we said it's important to focus on a small area very near the catalyst surface where the transport is actually taking place, okay, and it's taking place by a combination of convection and diffusion. The reactant has to come to the surface. The product has to leave the surface, and there has to be transfer of heat either to or from the surface depending upon whether the reaction is exothermic or endothermic. Okay. Let us look at the diffusion problem, the reactant going onto the surface. Okay. In this case, the fundamental quantity is the mass transported per unit time to the surface, because unless you transport that much mass per unit time to the surface, it is not going to get reacted and it is not going to come out. Okay. So, fundamental quantity is the mass transported per unit time to the surface. However, that depends upon things like the number of catalyst particles and so on. Okay. So, if you want to get an intensive quantity, something that is not dependent upon the total size of the system, then it is better to work with the mass flux. J is the mass flux, okay, and the mass flux has dimensions of mass transported per unit area per unit time. Okay. Mass transported per unit area per unit time. Okay. The mass flux to this catalyst surface in the mass transfer problem is going to depend upon the concentration difference between the catalyst surface and far away. Okay. The difference in concentration between the concentration on the surface of the catalyst and the concentration far away. That difference in concentration average has dimensions of mass per unit volume. Okay. And in all mass transfer problems, ultimately the rate of transport is going to depend upon the diffusion coefficient. Okay. The diffusion coefficient, last class we had actually derived the diffusion coefficient, okay, from the flux and the concentration difference, and the diffusion coefficient has dimensions of L square T inverse. Okay. If you recall, we said that the rate of transport of mass per unit area per unit time is equal to a coefficient times the concentration, mass per unit volume. From that we got the diffusion coefficient, and it is of course going to depend upon the diameter of the catalyst particle, okay, which has dimensions of L. Okay. In addition, the flow of the fluid very near the surface is of course going to depend upon the average velocity with which the fluid is being swirled around. Okay. So, it is also going to depend upon the fluid flow properties, which has an average velocity of the swirling of the fluid around it. Okay. And those fluid properties, the velocity u with dimensions L T inverse, okay, as well as the density and the viscosity. Now, there are 1, 2, 3, 4, 5, 6, 7 dimensional groups, okay, and how many dimensions do they contain? They contain 3 dimensions, and therefore, there should be 4 dimensionless groups. Okay. One dimensionless group is quite easy to see, okay, the Reynolds number. Then there is one dimensionless group which involves the mass flux suitably non-dimensionalized. Okay. So, the mass flux suitably non-dimensionalized, in this case we can write down the non-dimensional mass flux as the mass flux times the diameter divided by the diffusion coefficient and delta C. Okay. This is called the Sherwood number. Okay. And the third one involves the diffusion coefficient and some combination of the density and the viscosity. Okay. And you can easily see that this combination is mu by rho times the diffusion coefficient. Okay. Is equal to the kinematic viscosity divided by d, which is the Schmidt number. Okay. So, these are the different dimensionless groups. Okay. And once I know these three dimensionless groups, then I can find out the average flux to the surface, and from that I can calculate all of the quantities, okay, that are desired. Okay. Of course, beyond this one cannot go just by dimensional analysis alone, one has to go to correlations, okay, in order to find out what the diffusion coefficient is. Okay. And there are various correlations that are used in this problem. Okay. I will just briefly give you two correlations. One is that the Sherwood number is equal to 2 plus 0.6 Reynolds number per half times the Schmidt number per 1/3. Okay. This is in the limit of very low, okay, Schmidt number and Reynolds number, where the flow is basically in the laminar state. Okay. Now, if the Schmidt number is large, then I have a correlation of the kind Sherwood number is equal to 1.24, okay, Re per 1/3 Sc per 1/3. Okay. This is in the limit of high Sc and laminar flow. And you have other correlations, the limit of turbulent flows. Okay. There are various correlations that are proposed for turbulent flows through around a particle, okay, but we will see that a little later. Okay. But the point is that in all these cases you can get correlations between the Sherwood number, the Reynolds number and the Schmidt number. Okay. And these correlations have different forms in different regimes. Okay. In the laminar regime they have one form, in the turbulent regime they have another form. Okay. And the question that we will ask in this course is, why do these kinds of correlations come about, okay, in the flow past particles. Okay. I could do the same analysis for the heat transfer problem. Okay. I could do the same analysis for the heat transfer problem. Okay. And you will get correlations that are exactly of the same form. Okay. You will get correlations that are exactly of the same form, except that these correlations, instead of the Sherwood number, they would have the Nusselt number, okay, and instead of the Schmidt number, they would have the Prandtl number. Okay. There is a fundamental reason why correlations are of this form. The reason is because in all cases, whether it is heat transfer or mass transfer, the mechanism is the same. The Nusselt number and the Sherwood number are scaled fluxes. Sherwood number is a scaled mass flux, the Nusselt number is a scaled heat flux. Okay. The Reynolds number is the ratio of inertia to viscosity. The Schmidt number and the Prandtl number are the ratios of diffusivities of momentum to diffusivities of mass and heat respectively. Okay. And that is the reason that they all have the same form. Okay. We will come back to that in the next class and see why that is so. Okay. So, that is as far as the mass and heat transfer to this problem is to the particle is concerned. Okay. How about the power requirement for the impeller? Okay. So, let us look at the power requirement for the impeller. I have an impeller that is moving in it is rotating in a fluid, okay, and I want to estimate what is the power required for this impeller. Okay. So, what is the power? Power P is equal to rate of change of energy, rate of input of energy. Okay. Energy is mL square T power minus 2. The rate of change of energy is energy per unit time. So, this is equal to m L square t power minus 3. Okay. Okay. So, what does this depend upon? Okay. Of course, it depends upon the frequency with which the impeller is rotating. Okay. So, it is going to depend upon the frequency with which the impeller is rotating, okay, the frequency f. Frequency is number of rotations per unit time. So, it has dimensions of t inverse. Okay. It will depend upon the impeller diameter. Okay. It is going to depend upon the diameter of the impeller d. The larger the impeller, the more power is required. So, it will have d has dimensions of length. Okay. And then it depends upon density and viscosity. Okay. And there are two other things that it could depend upon. Okay. First of all, it could depend upon the total length of the tank, okay, which I will call small l. Okay. So, L has dimensions of length. Okay. In addition, as this impeller is rotating, this is going to cause the surface to deform. Okay. So, this is going to cause the surface to deform. Okay. The surface will curve upwards at the walls and downwards at the in the middle. Okay. So, this is determined by a balance between gravity, which tends to make the surface flat, the inertia which tends to push the fluid away, the centrifugal forces which tend to push the fluid away from the surface, as well as the surface tension. So, it could depend upon gravity, which is an acceleration, rate of change of velocity, okay, L t power minus 2, and the surface tension gamma, okay, which is m times t power minus 2. Okay. So, there are 8 dimensional groups out of which there are 3 dimensions. Therefore, there should be 5 dimensionless groups. Okay. And one of these is quite easy to see, that is the ratio of lengths. Okay. So, pi 5 is equal to the ratio of lengths L by d. So long as I keep the aspect ratio, as I do a scale up of this reactor, if I keep all dimensions proportional to each other, then this will not change. Okay. And then there are 3 other dimensionless groups. Okay. One of them is the power itself, okay. And the power I can scale it by the frequency, the diameter, and either the density or the viscosity. Okay. If I were to choose the density to scale it, okay, then my dimensionless group for the power is going to be equal to P by rho d power 5 f cubed. Okay. This is called the power number. Okay. So, this is the power number, which is the dimensionless power input to the system. Okay. And then there have to be 2 other dimensionless groups. Okay. One of them involves the density and the viscosity, and that is our familiar Reynolds number, except that this now has to be expressed in terms of the frequency. Okay. So, the Reynolds number expressed in terms of the frequency will be rho d f square by mu. I am sorry, this is going to be rho d square f by mu, okay, Reynolds number. Okay. And then I have gravity and surface tension. Okay. There have to be dimensionless groups which involve gravity and surface tension. Okay. So, the third dimensionless group, if we assume involves gravity, okay, it is quite easy to frame. This is just equal to u square by mu by gravity. Okay. This is called the Froude number. And there has to be one that involves surface tension. Okay. And that, once again, dimensional basis is quite easy to see what that is. This has to be rho d cubed f square by gamma. Okay. This is called the Weber number. Okay. So, I will finally get the power number is equal to some function of Reynolds number, Froude number, Weber number and L by D. Okay. So, there is a final relationship that I will get. Okay. And then further scaling will depend upon what these parameters are. So, for example, if I were considering in the limit of very small Weber number, okay, then I would consider that Weber number is not a parameter in the problem. Okay. So, surface tension is the dominant force, whereas if the Weber number is very large, surface tension is not important. So, I can neglect surface tension. Froude number, if ud by g is large, that means that the inertial forces are large compared to the gravitational forces. That means that gravity is not playing a factor, whereas if ud by g is small or order 1, that means that gravity is also important. Okay. And similarly, the Reynolds number, I can check whether it is large or small, and then I can get correlations in different regimes. These correlations have to be obtained for each different configuration. In other words, this correlation between the power number and Reynolds number, Froude number, Weber number will be valid only for that particular geometry. If I change the shape of the impeller, then I have to do the calculation once again. Okay. If I change the aspect ratio, that is the thickness of the impeller to the total tank size, then I have to do the calculation all over again. Okay. So, even though we can get up to this stage, okay, we cannot go further. Okay. And the question is, how do we go further in our analysis? Okay. In particular, firstly, what do these dimensionless numbers mean? Okay. I managed to get dimensionless numbers in just in terms of dimensional variables, but however, there is the question of what is the physical interpretation of these dimensionless numbers. Okay. Is there a meaning to them, or could I just choose it at random? Could I take the product of two different numbers and call that a new dimensionless number? If I did that, then what would that mean? Okay. So, I will spend the rest of this lecture trying to give you a physical understanding of what is the meaning of dimensionless numbers. Okay. How do these correlations come about? Okay. And then we will proceed to what is the procedure that is going to be used in this course for obtaining many of the same results that we have got here. Okay. In this course, we will focus in detail on at a microscopic level on the surface of a particle, say. Okay. Actually calculate the variation in velocity, concentration everywhere around the particle, and from that back out what is the relationship between the dimensionless numbers for the average flux for that particle. Okay. So, physical meaning of dimensionless numbers. Okay. Let us first start off with just the physical meaning of diffusion. Okay. In this case, we will be talking about the transport of mass, heat, momentum, diffusion of mass, diffusion of heat, conduction, momentum transfer due to stresses. Okay. But one can write down a diffusion equation for a general quantity. Okay. And the diffusion equation for a general quantity can be written as flux of quantity per unit area per unit time is equal to the diffusion coefficient into the change in density of the quantity per unit length. Okay. So, for example, if I had a slab of fluid, okay, across which I was applying a difference in concentration C1, C2, and the difference in concentration across a length L. Okay. Then the flux J was equal to D into delta C by L. Okay. Flux of quantity per unit area per unit time, flux of mass per unit area per unit time J is equal to diffusion coefficient D times change in the density of that quantity. Density is quantity per unit volume, that is the concentration. Change in concentration divided by the length across which you apply the concentration gradient. Okay. So, this is quite obvious for mass transport. Heat transport takes place by conduction. Okay. And if I have two temperatures T1 and T2 across a length L, okay, then the heat flux Q per unit area per unit time is equal to K into delta T by L. Okay, the heat flux is equal to K times delta T by L. Flux of quantity per unit area per unit time, flux of energy per unit area per unit time. The quantity is energy. Okay, so, flux of energy per unit area per unit time is equal to K delta T by L. This is not in the form of a difference in the energy density. The energy density, energy per unit volume, is going to be equal to rho Cp times T. Okay. The density, mass per unit volume, times specific heat times the temperature. Okay. So, the densities, so I have to write this as something times delta of rho Cp T by L. Okay. Change in the energy across energy per unit volume between the two phases, change in the energy per unit volume between the two phases. So, obviously, this has to have K by rho Cp. Okay. So, energy flux is equal to the diffusion coefficient times the change in energy density, okay, change in density of the quantity, that is energy density per unit length, okay, between 2 points. Okay. So, this change in energy density is equal to the thermal diffusion coefficient. Okay. How about for momentum transfer? Okay. For momentum transfer, okay, I take two phases. Okay. This is moving with the velocity u and this is stationary, and I have a linear velocity profile. Okay. Let us take a coordinate system x and y, okay. And the Newton's law for viscosity states that tau xy is equal to mu times delta u by the total length L. So, the delta u is the difference in velocity. Okay. Flux of quantity, in this case flux of momentum, momentum transferred per unit area per unit time. Okay. Flux of momentum is momentum transferred per unit area per unit time, which is rate of change of momentum is a force. So, flux is the force per unit area, that is the stress. Okay. So, this thing is the flux of momentum. Okay. That has to be written as something times the change in the momentum density between these 2 points. Okay. Something times the change in the momentum density. Now, momentum is mass times velocity, momentum density will be mass density times velocity. So, this will be del dot the difference in the momentum density times velocity, okay, divided by L, okay, and obviously the prefactor has got to be equal to mu by rho. Okay. So, the diffusivity for momentum is the kinematic viscosity. Okay. So, this is equal to nu times delta of rho u by L. Okay. So, the diffusivity of momentum is the kinematic viscosity, mu by the viscosity. Okay. So, expressed in this general form, right, I have a diffusion coefficient for mass, which is just the mass diffusivity itself. I have a diffusion coefficient for heat, which is the thermal diffusivity, it is k by rho Cp. Okay. And I have a diffusion coefficient for momentum, okay, which is viscosity divided by rho, the kinematic viscosity. Okay. And it is easy to see that all three coefficients, okay, mass diffusivity, which is d, has dimensions of L square T inverse. Okay. Thermal diffusivity, which is alpha, okay, which is k by rho Cp. Okay. You can work it out for yourself and you will find that this is also equal to L square times T inverse. Okay. And then there is momentum diffusivity, which is nu kinematic viscosity, which is mu by rho. That will also have dimensions of L square T inverse. Okay. So, all diffusion coefficients of any quantity have dimensions of length square time inverse, okay, provided I express the flux of that quantity in terms of the change in the density of that quantity per unit length. Okay. We will see later that this change in density per unit length can be written as a gradient. Okay. I should note that flux is a vector, it has a direction to it. Okay. We will see that later on in the course. I have been dealing with it right now as if it was just a scalar, but we will see later on in the course that flux is a vector which has a direction to it. Okay. And that is the direction. So, flux will go in the direction where there is a change in the concentration. Okay. So, the change in concentration upwards, the flux will go upwards. So, the change in concentration from right to left, the flux will go from right to left. Okay. That is true for mass flux, for heat flux. Okay. Momentum flux is a little more complicated because momentum itself is a vector. We will see how to deal with that later. Okay. So, I have explained to you what is the rate of diffusion of different quantities. Okay. Now, what is the rate of convection? Okay. If I have some pipe with some cross section and there is a velocity field going across this pipe. Okay. Convection gives you the rate at which the material is transported from left to right due to the mean fluid flow. Okay. So, if I have the density of some quantity, let us say the mass density as concentration. Okay. So, mass density, which is basically the concentration locally. Okay. The flux of material transported across a surface area per unit time is going to be equal to the velocity, okay, times the concentration. Okay. That is because the total amount transported okay, if I have some surface area, let us say S, the total amount transported is going to be equal to the velocity times S times the concentration. Okay. And therefore, if I divide by the surface area to get the flux, I will get just the velocity times the concentration. Okay. The rate of diffusion is equal to d times delta C by L, where L is the characteristic distance. Okay. It is the particle diameter in the case of the flow past a sphere, it will be the tube diameter for the diffusion happening across the flow. Okay. Therefore, the ratio of convection by diffusion will be equal to U C by d delta C by L, which will be approximately equal to U L by d. Okay. So, this is the ratio of convection to diffusion, okay, in all of these problems. Okay. What are these dimensionless numbers? Okay. Previously, for mass transfer, okay, I had said that the dimensionless number was the Schmidt number, which was mu by rho times the diffusion coefficient. Okay. This is equal to the kinematic viscosity divided by the momentum diffusivity. Okay. So, this is equal to momentum diffusion by mass diffusion. Okay. The Prandtl number Cp mu by k. I can write this as mu by rho times rho Cp by k. Okay. Mu by rho is the kinematic viscosity, nu the momentum diffusivity, and k by rho Cp is the thermal diffusivity, alpha. So, this is equal to momentum diffusion by thermal diffusion. Okay. So, that is the Prandtl number. Reynolds number, the Reynolds number that I had calculated earlier was rho u d by mu. Okay. This can be recast as u times d by nu, because mu by rho is the kinematic viscosity. Okay. So, this is going to be equal to convection by momentum diffusion. So, the ratio of inertia and viscosity can also be thought of as the ratio of convection and momentum diffusion. Okay. From these I can get other dimensionless numbers. Okay. For example, I can get a Peclet number is equal to u d by the mass diffusion coefficient. Okay. And you can easily verify that this is equal to Reynolds number times the Schmidt number. Okay, is the Peclet number. So, convection by momentum diffusion times momentum diffusion by mass diffusion gives you convection by mass diffusion. So, this is the Peclet number for mass transport. Okay. One can write a similar Peclet number for heat transport. Okay. So, the Peclet number for heat transport will have the form u d by alpha. Okay. This will be Reynolds number times the Prandtl number. Okay. Reynolds number convection by momentum diffusion, Prandtl number momentum diffusion by thermal diffusion. So, this is equal to convection by thermal diffusion. Okay. So, the fundamental numbers can be written in this way as either as a ratio of convection and diffusion or a ratio of two diffusion coefficients. Okay. All of the numbers on the right hand side, okay, that I had got here, the Reynolds number, the Schmidt number for mass transfer as well as the Prandtl number for heat transfer can all be written as the ratios of convection and diffusion or the ratios of two diffusivities. Okay. There are the other numbers which are dimensionless fluxes. Okay. We have already seen two of those. Okay. The first was the Nusselt number, which was q d by k delta t, okay, which is a dimensionless heat flux. Okay. And then we saw the Sherwood number, which was j d by the diffusion coefficient times delta c, which was a dimensionless mass flux. Okay. So, all of the correlations that we have seen so far are correlations which relate these dimensionless fluxes, dimensionless heat flux, dimensionless mass flux to the ratios of convection and diffusion of momentum, the ratios of diffusion of mass momentum, the ratio of diffusion of heat and momentum. Okay. So, to summarize what we have done so far, we first looked at the heat transfer problem, the heat transfer in a heat exchanger, and we first started doing it simplistically, the way that we normally do it if you were just given a dimensional analysis problem. We listed out all the dependent variables, the heat flux, the specific heat, thermal conductivity, temperature difference, as well as the various mechanical parameters that can affect this, the tube diameter, the density, viscosity of fluid, fluid velocity and the length of the pipe. And we made one simplification. We said that since the thermal energy and mechanical energy cannot be interchanged, we can consider the thermal energy as one fundamental dimensional group. Okay. So, that has increased the number of dimensional groups that we have and reduced the number of dimensionless groups down to 4. Okay. And we got q d by k delta t as one dimensionless group. The Nusselt number is a function of the Reynolds number, the Prandtl number, and the ratio of d by L. Okay. And correlations are available in literature in various regimes which tell you what this relationship is. Okay. In a similar manner, we looked at the heat transfer and mass transfer from a catalyst surface in the reactor problem. Okay. And in that case, the mass flux is related to the difference in concentration, the diffusion coefficient, as well as the particle diameter, the mass, the velocity, density, and viscosity. Okay. And on that basis, we got a relationship between the dimensionless mass flux, which is the Sherwood number, and two other parameters, the Schmidt number and the Reynolds number. And I said these correlations are available in literature. If one were to solve the same problem, okay, for the heat transfer, one would get the exact same correlations, except that one would replace the Nusselt number instead of the Sherwood number as the dimensionless flux, and Prandtl number as the Schmidt number. Okay. And we saw a little later, based upon what are the physical interpretation of the different dimensionless numbers, why that is so. Because I can write the flux of any quantity per unit area per unit time as a diffusion coefficient times the change in the density of that quantity per unit length. And straight away, since the quantity has the same dimension on both sides, the diffusion coefficient will have dimension of length square T inverse. I have a per length square per time on the left hand side, and I have 1 over length cubed for the density and 1 over length. So, I will get length square times T inverse. Okay. And we calculated the diffusion coefficients for mass, heat, and momentum. Okay. And similarly, I told you that you can get diffusivities for mass, heat, and momentum. The convective part just goes as u times the quantity. Okay. The flux of due to convection just goes as u times the quantity. On that basis, we got dimensionless groups as the ratios of convection and diffusion, or the ratios of two different diffusivities. Okay. We will use this framework in order to broadly classify all dimensionless groups and all the correlations that are obtained for transport processes in the next class, before we proceed with how we are going to start doing the analysis in the next class. Okay. So, kindly keep in mind the different dimensionless groups and their interpretations, okay, and we will start from there in the next class. Thank you, and we will see you next time.